Thank you so much for joining us today. My name is Mia Burke, and I'm Program Manager with Hanford Challenge. Hanford Challenge is a nonprofit based in Seattle that focuses on cleanup of the Hanford nuclear site and supports insiders, workers, and whistleblowers who have issues that are not being addressed. This is the 13th webinar of our Nuclear Waste Scholar Series. We started the series to inspire action and involvement with Hanford cleanup by inviting movers, shakers, and thinkers to share groundbreaking scholarship, art, research, and experience working with nuclear waste. It is my pleasure to introduce our speaker, Dr. Arjun Makhijani. Dr. Makhijani is president of the Institute for Energy and Environmental Research. He holds a PhD in engineering from the University of California at Berkeley. He has produced many studies and articles on nuclear fuel cycle related issues, including weapons production, testing, and nuclear waste. He is the principal author of the first study ever done on energy conservation potential in the US economy. Dr. Makhijani is the author of many books, including Carbon Free and Nuclear Free, a roadmap for US energy policy. His most recent book is Exploring Tritium Dangers. Just as a heads up, Dr. Makhijani's presentation will be about 35 minutes long, and we will leave time after the presentation for Q&A. We do have a hard stop at 1 p.m. If you can't stick around for the whole time, feel free to leave. We will be recording the presentation, and we'll share a link of the recording with everyone that registered. Thank you so much for joining us today, Dr. Makhijani. I'll pass it to you to talk about your work.
You're welcome. I will share my screen. So I said to myself in 1989 that I really had written enough about nuclear waste, enough, there was a book, High Level Dollars, Low Level Cents. And unfortunately, I wrote more after that. And the problem goes on, and we're still dealing with it. And we need to deal with it much better. I'm going to give you a little survey. My task was to kind of look at managing radioactive waste. There's a lot of it, so many different kinds. So I'm not going to cover the whole waterfront, but at least let me show you how many different kinds we're talking about. There's military and civilian. There's the processes, uranium mining, milling, uranium processing into fuels, depleted uranium, reactor spent fuel. I feel like, one of the reprocessing wastes, low-level waste, transuranic waste, military low-level waste, greater than Class C waste, decommissioning waste. Then there's a question of, long-lived radionuclides, short-lived radionuclides, medium radionuclides. By short-lived, it could be seconds or days. By long-lived, it could be millions of years half-life. Medium is like cesium, the cesium-137, about a 30-year half-life. Now, the health and ecosystem risks. I'm not going to talk about that today. You can ask me questions, but I'm going to talk more about management. I'll mention health and ecosystem risks. It depends on the amount of radioactivity, the composition, the specific radionuclides, what ecosystems it's in, the form of the waste, and so on. Then there are security risks. Then our spent fuel has a lot of plutonium in it. So this is a uranium surface mine. And surface mines, as well as deep mines, have a lot of waste at the mine site. So you're trying to get at the ore, which could be, 0.4, 0.5% uranium, 1%, 2%. That would be very good ore. The Congo ores had, 40, 50% uranium, something like that, almost about the purest uranium ore that has ever been found. But at the site, when you have underground or surface mining, you have overburden, you have mine wastes, and those mine wastes don't contain extractable uranium, but they contain higher uranium than what's in the dirt, which is 1 or 2 picocuries per gram. And so we have a vast amount of mine wastes at the mine sites. And as you probably know, there are 500 abandoned mine sites just in the Navajo Nation in the Four Corners area. and there are many others. There's also solution mining where you can't see the waste, but there's because you're re-injecting the radioactivity underground, but you're making it mobile. When you extract the uranium from the ore, you get, so the ore is like, let's say 1%. So for every ton of ore, you only get 1 ton of uranium. About 1/10 of that goes into the mill tailings. And so mostly you have this sandy material that contains uranium, radium, thorium-230, radium-226, the whole uranium decay chain of radioactive materials, which is quite a long decay chain. And thorium-230 has a half-life of 75,000 years. So mill tailings will last a very long time. 200 million metric tons or more of it is in the United States, mostly in the Colorado Plateau, New Mexico, Arizona, Colorado, and Utah. This is a mine, mill tailings in Colorado. In the late 70s, these mill tailings were moved to lined ponds. And the liner is supposed to last for 1,000 years. So here's one of the dilemmas. This stuff contains thorium-230, which is part of the decay chain of uranium-238, which is 99+% of uranium ore, natural uranium. Thorium-230 has a half-life of 75,000 years. It decays into radium-226. So long as you have thorium-230, you're going to have radium-226. So long as you have radium-226, you're going to have radon and all the decay products of radon. The EPA said, we're going to put these mill tailings into lined ponds. Good, better than contaminating all the groundwater underneath, as was going on in this place. Leaching acid, sometimes it's acid mill tailings, sometimes it's basic high pH or low pH mill tailings, all corrosive, all contaminant, if it reaches the groundwater. But the liner is supposed to last for 1,000 years, and the half-life of thorium, which is the source of all of the decay products downstream of it, including radium and radon, is 75,000 years. This is a problem that has been swept under the rug. Yours truly has tried to kind of lift up the rug, but very few have yet seen it. So far been unsuccessful. Maybe, I don't know of a good solution to this problem, but I think that we won't have a good debate about it if we don't recognize that this stuff is as much forever as spent fuel. And we need to deal with it because it is going to be a problem in the long term. Sometimes the liners tear when they're installing them, so it's not just the long term. It's already a problem in some places. So when you take uranium, you make it into yellow cake, and then you make that into uranium hexafluoride and you enrich it. So uranium fuel that we used is 4.5% uranium-235. Most of the uranium, 99.3% of the uranium, natural uranium, is uranium-238. So you got to enrich it. When you have more uranium-238 on 235 on one side, enriched in the material that gives you the chain reaction, uranium-235, then you have depleted uranium on the other side. So every kilogram of reactor fuel that we have, today's grade of reactor fuels, you get 7 or 8 kilograms of depleted uranium. We've got 500,000 tons of this stuff. This is uranium hexafluoride. It releases some small quantities of hydrofluoric acid, pretty corrosive. These are 14-ton cylinders sitting around in Portsmouth, Paducah, Kentucky, Portsmouth, Ohio, and Oak Ridge, Tennessee. The Department of Energy is processing some of this stuff into a more stable oxide form, and that is a good thing. But then you get hydrofluoric acid waste from that, and that is an issue. So spent fuel is the used fuel from nuclear power plants. Almost all so the vast volume of waste is the mine wastes and mill tailings. More than 400 million tons of it in the United States, even though the United States is importing roughly 85, the mid 80s% of uranium fuel requirements being imported from other countries, Russia, Kazakhstan, Namibia, a variety of countries, Canada, Australia, variety of countries. And of course, in Canada and Australia, a good bit of it comes from indigenous lands. And when the fuel no longer efficiently generates electricity or heat, it's taken out, it's very hot. That's why you have to cool it. This is kind of the swimming pool size structure in which the spent fuel is stored. The spent fuel is underneath. You have to have, I don't know, 10, 12, 14 feet of water on top to protect the personnel from the radiation. That blue glow is called Cherenkov radiation as a result of radiation being emitted from the spent fuel. Now, some of the spent fuel is stored in a variety of casks. There's vertical, there's also horizontal. I have a slide of that. So we've got about 90,000 metric tons of this stuff. That's the map. Most of it is in Illinois, much is in Illinois, Pennsylvania, the Southeast, Texas, so on. I'm showing you pictures mainly. So in the Manhattan Project, the Hanford plant was built. The uranium for the Hanford plant came from downtown St. Louis, whether you know that or not. The ores were sent there. Some of it was also processed in Iowa, the university there, Iowa State University, I think, Ames. And uranium metal production was a new thing at the time. There was a fair amount of contamination. That whole waste, some of that Manhattan Project waste is currently a risk in the Westlake landfill in St. Louis. And there's radon emanating from it. They took it from downtown, they dumped it. It was called airport cakes, dumped it in the airport, and they took it from there and put it in a landfill called the Westlake landfill. There's part of it is municipal waste, part of it is hazardous, part of it is on fire, part of it is radioactive. Just a long discussion with a reporter about the radioactive part about that landfill yesterday. And nobody knows exactly, what to do. And the moms and the families living next to it are worried. And more than worried. They're living with the risk. These are high-level waste tanks. Now, this is a saga I want to dwell on a little bit. Now, all of you are probably aware, attending a Hanford Challenge event, that Hanford is the biggest radioactivity mess in the United States. In some ways, the most complicated radioactivity mess in the world. Why is it a complicated radioactivity mess? So this was built during the Manhattan Project. The reprocessing plants were built in the 1943 and 1944. The first one was started up in late 1944. I can't resist a very sad historical note. So the United States started its bomb program, and therefore Hanford, because of the fear that if the Germans got there first, Hitler would have a monopoly of the bomb, and that would be a bad thing. Pretty much everybody was agreed on that. I have said, if I had been alive at the time, I would have also agreed on that. And I didn't have more wisdom than Einstein, I'm sure, because he signed off that saying we should do something like this. But in early December 1944, the Manhattan Project, which had its own spy mission to Europe, found out that Germans don't have a viable bomb project. And no less a physicist than Richard Feynman, who was there at Los Alamos during the Manhattan Project, but didn't leave, unlike Joe Rothblatt, who was the only one who left. In 1980, he said, he wondered, I think he said something like, it was immoral to stay because our job had been done and we knew Hitler didn't have, but we stayed. And he ended his interview with the BBC by saying, I wasn't thinking, okay. Plutonium, the reason to tell you this long story is the purpose of the project in terms of the Germans had been accomplished. Plutonium separation, and therefore all the waste that went into the 177 tanks at Hanford, none of that had been produced as yet. The reactors, I think, were started up in early December. Please check that. But the reprocessing plants were not started up until later that month. So none of the 58 million gallons of mess, which is now estimated. So I'll tell you so what happened then is plutonium separation involves dissolving the fuel in acid and separating the uranium, which is most of the spent fuel or irradiated fuel, from the plutonium. In military irradiated material, it's a fraction of 1%, the plutonium. And that's what was going on here. And this acidic waste requires stainless steel tanks to store, otherwise it just eat right through the tanks. So instead of that, they neutralize the waste with lye, sodium hydroxide, and potassium hydroxide, one or the other or both, and greatly increase the volume of waste, increase the complexity of the waste, the physical complexity of the waste, and put it in carbon steel tanks because stainless steel was in short supply during the war. I think during the war, if you're going to make plutonium, that was a reasonable technical decision to make. But nobody revisited it at the end of the war. Say, unlike Idaho, where they had reprocessing, they built stainless steel tanks. The French do reprocessing in their commercial sector. They built stainless steel tanks. So they store acidic waste and have done it successfully. But in the United States, the plutonium production sites at Hanford and Savannah River neutralized their waste and greatly complicated life. And part of the management mess is a result of that. And it really, at Hanford, it is more of a mess because in the Manhattan Project, the uranium was coming from Congo, Canada, various places, some even from the United States, I think. And the uranium was just dumped as waste in these tanks. They were after the plutonium in a hurry to do the Trinity test. And then after the war, they wanted to get the uranium out. They did that in the 50s, and that made more of a chemical mess. So the history of the Hanford tanks, just from the science and technology point of view, is very complicated and very difficult and compounded by not very thoughtful management. So let me come to almost 95% plus percent of the radioactivity in waste is in spent fuel from nuclear power plants. We've got about 90,000 tons of it. By the time we're done retiring the reactors we have, it's going to be considerably north of 100,000 tons. So we start with 4 or 4.5% uranium-235. That's the enriched fresh fuel. 96% is uranium-238. It had no plutonium, no fission products. By the time you're done, you still have a little bit of uranium-235 left. You have a new isotope of uranium-236. This one makes it a little bit more complicated to reuse the extracted uranium. So in principle, you could say, well, it's uranium, you could, re-enrich it. The spent fuel also contains plutonium. Today's spent fuel contains about 1%. In the older days, when the enrichment was 3.5%, it was less than 1%, maybe 0.9 or something like that. So about 4.6% of the fuel fissions, and that's almost all the radioactivity. And then you have neptunium. And so let me give you a little survey of the half-life. So plutonium-239, which is most of that 0.99, these are fractions. No, percent. Yeah, no, these are percentages. I'm sorry. Plutonium-239, half-life 24,000 years. Some fission products are very short-lived. Iodine 131, 8 days. Iodine 129, 16 million years. Same danger, but a large mass to make a little bit of radioactivity. Iodine 131, a small mass to make a lot of radioactivity. So radioactivity per unit weight is inversely proportional to the half-life. Long half-life means it's going to be around to mess with the environment and health for a long, long time. Short half-life means it goes away, but it's a much, much bigger danger. That's why iodine 131 was a very big danger during nuclear testing in Nevada, for example. Then we have non-plutonium transuranic materials. They're not there in the fresh fuel. Most of this is neptunium and americium. Americium comes actually from plutonium-241. It's a decay product of plutonium-241. It builds up. It has a half-life of 432 years. And neptunium-237, which builds up during the reactor operation, has a half-life, if I'm remembering correctly, of 2 million years. And uranium-238 has a half-life of I think 4 billion years. U-235 has a half-life of 700 million years. So you're talking forever, basically. All right, so this is the situation with spent fuel overall. This spent fuel has got 800 metric tons of plutonium in it, roughly. That's about 10 to 15,000 nuclear bombs worth. Now, in the United States, very little commercial spent fuel was reprocessed. We have some plutonium in the civilian sector, but in other countries, France, Britain, Russia, India, Japan, those are the main ones. Much more reprocessing has happened. Today, there's more than 300 metric tons of separated plutonium. It's about 5 to 10 kilograms. So about 100 to 200 per metric ton. So 300, multiply that. So you're talking 30,000, 3,000 to 6,000 bombs. I did my mental math right there. So there's more separated plutonium in the civilian sector than in all the nuclear weapons, in all the nuclear weapon states put together. It's become a management problem because it's very expensive to use it as a fuel. There's more than 100 metric tons just sitting at Sellafield. And there's more than 80 metric tons, maybe 90. I don't have the current numbers, but more than half of it is in Britain and France. And then you've got these 4,000 metric tons of highly radioactive fission products. Most of it, the radioactivity is in strontium-90 and cesium-137. So medium half-life, so they're around for hundreds of years, posing risks. And the one radionuclide I want you to pay attention to, if you can see my arrow, is this one, cesium-137. I'll tell you why a little bit later. All right. So that's the situation. In the short term, moving this stuff has its risks, I'm not going to dwell on that. It's being stored, as I've shown you, in spent fuel pools, which is necessary for a few years. But we need to harden the storage. There's the risk of accidents and malevolent acts. And we know that since 9/11, that this is a serious risk. And many people around the world have advocated hardening the storage, reducing the off-site signature. So what do I mean by reducing the off-site signature? So spent fuel is hot because of the radioactivity. It's generating heat. Heat has an infrared signature. So, you have infrared guided munitions. And so if spent fuel is sitting around like this, this is giving an infrared signature. It's sitting around on lakes, lakefronts and ocean fronts and river fronts. Not a very good thing, in my opinion. Hardening storage would mean it'll be much more difficult to tear into it. It'll be difficult to, target it with infrared guided munitions, things like that. Reprocessing, has been advocated. Some people say, well, you reduce the volume of high level waste, you reprocess it, you make it into vitrified logs, as the French have done. So I've looked at the French waste system. I do speak French. I've led 2 teams evaluating their repository program. They are there in French on our website, and English summaries, I think, are available. This was from about 15 years ago. These were sort of official evaluations that we did at the French official stakeholder group requests. So it's true that the vitrified, when you take that acidic waste and vitrify it, as they have also done at Savannah River, they vitrified part of the waste. The vitrified waste is about 70% of the volume of the spent fuel. But now when you do the processing, you have a lot of highly plutonium contaminated transuranic waste. You have what's called low-level waste, but it's so radioactive with so much long-lived radioactivity in it, fission products, that you have to dispose it off in a repository. And this is a French regulation. I'm not making up my own rules here, although I've advocated what rules I would like to see. So when you add up how much you have to put in a repository, it's about 7 times the volume of spent fuel. And these are DOE numbers from a while back, 15 years back, something like that. And then, of course, with this separated plutonium, you got a proliferation risk unless you use it as a fuel, in which case now you have spent fuel that has more plutonium in it than what I showed you, several times more. So you're not solving the problem. You're trying to pretend. It's pretend solving the problem. In fairness, I should say that reprocessing was advocated when people thought we will have these sodium-cooled breeder reactors and we'll be able to use all the plutonium and we'll be able to use all that depleted uranium and we can stop mining. Well, that didn't work out. We've spent $100 billion worldwide. By we, I'm speaking as a global citizen here, trying to commercialize breeder reactors and the whole plutonium economy, and failed. Now, I've already told you how much plutonium there is. Hanford is a mess. So let me tell you, in 1997, we did a study called Containing the Cold War Mess. The link is there under this slide. I'll send you the slides. And the Department of Energy was very good. They said, you've done a very valuable report. We had a joint press conference in releasing the report. The only one I think I did jointly with the DOE. They said, we'd love to cooperate with you to fix our remediation program. And one of the meetings we had in my office with the DOE around 1998, and it was very cooperative and very cordial because we're all trying to solve this problem, right? And so I will often say, if I think, far too many bombs. So if you want to make more bombs, we won't agree because I think we shouldn't be making more bombs anywhere, not in the United States, not Russia, not anywhere. But if you're trying to remediate contamination, we can be on the same page because we have the same goal. So that was the spirit. At that time, they had said they're going to build this giant waste processing plant, and then they will vitrify the waste. I told them, you haven't characterized. Hanford wastes are chemically and physically complicated. The DOE themselves had, I think, described. So the waste consist of pretty like liquids like water with low viscosity, cement-like hardened material, highly radioactive, and everything in between, some of which was described by the DOE once as peanut butter consistency. You wouldn't want to eat it, of course. I told them, and it's hard to sample many of these tanks because they're generating hydrogen, and any spark could result in an explosion. And so these tanks are not well, or were, the last time I looked, which was some time ago, they're not well characterized. I believe that is still the case today. Mia, correct me if I'm wrong. But a large number of tanks remain to be. My point was, you don't know what's in the tanks, so you can't build a one-size-fits-all processing plant. You should build a plants with many different chemistries that are much smaller in explosion-proof buildings, and then decide which of these chemistries you're going to use once you start pulling the waste out of the tanks. And make these buildings explosion-proof, because if you have a problem, then at least you won't lose the whole game. And I told them, your contract with British Nuclear Fuels, which you have now, is going to fail, very likely. And this is, of course, hearsay, so you'll please, I'm not naming anybody. And they said, we recognize this is risky, but we can't stop it. And that contract did fail. The plant that was built did fail. And here we are 25 years later. And what I told them to do was to take into account the risk of failure and to build redundancy, and also to build different chemistries according to what we knew. So even back then, some of the tanks were characterized. We knew a fair amount about the waste. In the 90s, the DOE did do something of a good job in sampling and so on. And a lot of good work was done in the 90s, so don't mistake me. So often when I think about Hanford, I feel like Bernard Shaw. There's a recording of it somewhere, probably on the internet. I have heard it. A reporter said, "What should we do?" And he said, "I told you the last time I was here and you haven't done it." And I'm very sad to say that that is the case with the Hanford mess. Okay, so what should we do? So I'm only going to, I can't tell you what to do with the uranium mining, and the mine waste need to be cleaned up, and you know, and the EPA needs to attend to it, and it's a complicated problem. I'll talk about the spent fuel and the vitrified waste from the military side. So we need to do hardening of storage on site. I think the Savannah River vitrified storage is actually a pretty good example of hardened storage. You can't do that everywhere, but it's pretty good. I've seen it a long time ago, and I thought they did a pretty good job. So I'm trying to be fair. You know, you have to call out when it's done right, because we're trying to do this right. So some people advocate that we should store this on site for the long term. So take a nuclear plant on, say, Lake Michigan. You're going to not have funding for this after some time. There's going to be nobody, you know, you may lose your guns and guards at the gates. And remember, I told you to think about cesium-137, half-life 30 years. So today, those casks that are stored at nuclear power plants, you know, if you try to steal, put it on a truck and steal it, and then try to pull the plutonium out of it, when you try to pull the plutonium, the radiation will kill you. It has to be handled remotely. It's very difficult. It's very complicated. And the equipment to extract the plutonium all has to be remote. And it can be done. Of course, it is being done, you know, by nuclear weapon states, or has been done for a long time, but it's extremely hard. And for third parties and non-state parties to do it, I would say bordering on the impossible. After 200 or 300 years, there's only one radiation barrier between somebody who would extract the plutonium that's very big and being able to do it easily. That's cesium-137. Cesium-137 mostly gone. If you lose institutional memory, and remember, fancy areas of Washington, D.C., they lost institutional memory of chemical weapons within well under 1 century, about 50 years. So this is right in Washington, D.C., in a fancy area where quite wealthy white people live. Not to talk about the remote areas and, you know, where there are not much habitation, etc. You lose one set of spent fuel into the lake, you've lost the lake. You've lost Lake Michigan from one nuclear power plant. And so this is, the DOE has done this in its no action Yucca Mountain EIS. You can read it. You've lost the Mississippi River. You've lost the oceanic ecosystem. You don't want to do this. We cannot risk, and if you say we should have an institution, say like the church and so on, I need only point to the recent woes of the church in terms of the corruption of its supposed mission. And I don't think that's going to work either. So there's no good solution. Deep geologic isolation is the least bad that we have. Now, it's not disposal in underground. There are three technical pieces to an isolation system, and all three are important. So there's the geology, if it leaks into the rock, will it hold back the radioactivity? Yucca Mountain was pretty bad for that. By contrast, the French site, intact rock, is pretty good, the one in the east. But you can't magically introduce spent fuel into the repository. You have to make a mine. That's been the dominant design other people have explored, like vertical boreholes, all that. But you have to drill, dig, make a mine. That's been the dominant concept. Once you've made a mine, you have destroyed the original geology. Now you got to put very hot waste in the geology, and you have created a lot of joints. So the best example of a good geologic repository design was in Sweden. They were going to put copper canisters in a reducing environment. It would have preserved the copper for, hundreds of thousands of years. But what happened is when you dig a mine, now the water is no longer reducing. You've introduced oxygen, there's air when you make a mine. And then if you seal it back up, when is the original environment going to reestablish itself? You've got all these joints. Will it rain through and introduce oxidizing water? And they found it was much more complicated than the original evaluations. It's still the best example there is, in my opinion. But so you have to think about so the French site, for example, you can see when they drill holes in it, you have to have pretty big holes. Spent fuel would have holes that are a couple of meters, I think, in diameter. These vitrified wastes are less than a meter. And so when they make these big holes, the rock starts to fracture. Now you got a problem, because now you got pathways for the fission products to leak. So while the spent intact geology is good over there, the fracture situation, not so good. And then you have to fill it back up and seal it. And what I learned from the experts in this area, a very brilliant expert, Jack Damon, that I was privileged to work with, he taught me that this sealing business and figuring out what to do is really complicated. So you got to work all three things out. You have to evaluate each system. So you have to provide redundancy. My stance has been, you should design it so the containers will contain it all to the required standard. And if it leaks, the geology should be able to hold it back by itself to the required standard. So what I told the Blue Ribbon Commission, this is from my presentation to the Blue Ribbon Commission, that don't start citing. You haven't done the science. We have lots of ways to figure out what combinations of those three elements will work and what combinations will not work. Do that for a decade, then say, here are the sites that will not work with any reasonable combination of sealing and containers, so we're going to rule them out. Here are the sites that may work, and here are the sealing systems, and here are the type of containers. And we are going to establish a radiation protection standard beforehand, so we're not shifting the standard around as they did with Yucca Mountain. Yucca Mountain would not have met the 1989 standard. And then the Congress said, well, establish a special standard for Yucca Mountain. I called that the double standard standard. Not a good way to do this kind of problem. And the Department of Energy has failed in its repository mission. People don't have trust in it, confidence in it. And reestablishing trust is a very complicated and difficult situation. And an independent body would do much better. That hasn't happened, obviously. So we are in a place that's actually farther behind in this respect than we were in 1983 when 1982 when the Nuclear Waste Policy Act was passed, and 1983 when the National Academies published a study paid for by the DOE called the Geologic Isolation of Nuclear Waste. It's a brilliant study. It was the panel was chaired by Professor Pigford, who was one of my professors at Berkeley. He was a man of great integrity. We didn't agree about nuclear power, but he was a man of great honesty and integrity, and he was very frank about all these problems. He actually wrote a dissent to the Yucca Mountain Standards report, and I helped him get it into the New York Times. I was very proud to have done something for him. He had done a lot for me. And so I'll stop there and try to answer at least some of your questions.
Thank you so much, Dr. Makhijani, for sharing a ton of information in a very short amount of time.
Sorry.
I'm going to start with the Q&A that's in the box. And if people want to, it's easier if you add it there, but if you can also add it to the chat. And the first question is, DOE has recently embarked on an effort to pursue a consent-based siting program for identifying acceptable locations throughout the US for spent nuclear fuel, intermediate and permanent disposal. Do you support this program, and do you believe it will be successful in finally identifying?
I don't support it. Even if they identify a site and put the waste there, I don't support it. And this is in my slides. I'm going to send you my slides. You can post them, Mia.
Great.
That I think consent-based must be informed consent. What does that mean? That means doing the science first, because right now you're going to the community without the knowledge of what sites the triple elements that are required may even work. So it's not that we don't know anything. A lot of work has been done. We know Yucca Mountain is a bad site. Why do we know Yucca Mountain is a bad site? Because there's a significant risk that the containers may rust. And they may rust in 100 years or 1,000 years. We're not quite clear, but we know that the containers planned for it would rust. So container and geology don't match. So it doesn't meet, and you would rule it out. The French actually ruled out a site. I respected them for doing that, saying, not a good site, we're not going to do it here. And so if you don't do that science, then you should not go to the community and say, we're going to get consent, because you're going to get a result that will be an environmentally and socially unjust result. Yeah, there's something about, rural areas and isolated areas. I didn't have time to cover that, but that's a whole nother discourse as to where it should be put, whether it should be put in isolated areas or not. That's a question in my mind anyway.
Mm-hmm. Yeah, thank you so much.
So I think consent, this is not informed consent.
Yeah. What is the chemical complexity of spent fuel, and is it as complex as the waste in Hanford's tanks?
No, the spent fuel is fairly straightforward. It's of uniform composition, because when you make uranium into fuel for the present style of reactor, it's a ceramic pellet. It's uranium dioxide. It's a single chemistry. It's a pellet about like that. And then there's pencil thin rods, 10, 12, 14 feet, I forget the number, and then bundles of rods. And so it's a pretty uniform chemistry. And then it's clad in zirconium. So, that's a different material. So you have to get rid of the fuel rod somehow. And that is, so you have to break that open if you do reprocessing. And if you don't do reprocessing, one of the advantages of not doing it is you're putting the ceramic pellet, which is in a good decay resistant form in terms of chemistry, in a metal tube, which is a second barrier, and then you're putting it in a container that is a third barrier, and then you have the engineered barrier around the container that's a fourth barrier. So it's fairly straightforward. Hanford tanks are the very complicated chemistry. They've got ferrocyanides, they've got hydroxides, they've got it's because a lot of things were done chemically and chemicals were added and it hasn't been processed. Part of the processing was to make the chemistry uniform, to convert it into oxides, and then you can put it into molten glass. Because like your crystal for your wine, it's actually lead oxide glass. And so basically you're trying to convert all these materials into an oxide and put it into glass if that's the route you're going. But here you already have a ceramic pellet. You don't need, so that's one advantage of spent fuel disposal. Straightforward chemistry. Not straightforward to predict for 100,000 years, but straightforward chemistry.
Thank you. Contradicting reports reveal risks to the dry casks currently used in the US to store this waste. Can you speak on the nature of dry cask construction in our country, in the US?
Well, there's been all kinds of dry cask construction in the United States. The very first ones were good, actually. They were the German Castor casks. They're made out of metal. They're quite durable. They have a monitoring inside. So if there's a leak problem on the inside, you know that the contents are not intact. So when you make these dry casks, you have to fill it with an inert gas. So you're not going to fill it with air because oxygen could corrode the metal. And now you don't want that gas to leak. And so it's pressurized. So it will be really good to have a little pressure detector to know if you have a leak. To my knowledge, most of the casks, or maybe all of them that are being built now, don't have this. And so when time comes to take it out, put it in a transportation container. So you don't have an essential safeguard. I'm just thinking out loud, Mia. It recalls the British Petroleum not wanting to install $500,000 device, that blowout detector. They said, we're going to save $500,000, and then we had this giant problem. It's the dollars and cents may not be exactly the same, but good casks are available, and the United States Nuclear Regulatory Commission is choosing not to require them.
Okay, thanks.
Now, the existing casks vary in quality, and I'm not going to go into right now because I haven't refreshed myself, so don't ask me.
Okay. What is the volume of uranium tailing water that is being held in the lined ponds?
I don't know. I think pretty much everything must have been transferred. Last I looked, which was some time ago, it was more than 200 million tons.
Okay.
And there's a similar amount of uranium mine wastes. So not a lot of radioactivity, but a vast amount of material that are going to pose significant health because it's mobile, it's acidic, it's out in the open, it's getting radon. So when you have these lined ponds, you have to keep it covered with raw water so that the radon doesn't escape. And then the liner is so that it doesn't seep into the groundwater. So you got to protect from the bottom, you got to protect from the top. Now you're in the middle of desert environments, you're keeping these acres and acres, covered with feet and feet of water. It's going to be interesting when they have a Colorado River, whether there's a fight over this, please keep the water over the mill tailings. Not safe to have mill tailings that are dried out. Certainly more important than golf courses, I think.
Yes, definitely.
Sorry to be tongue in cheek, but
What do you make of this latest development? And it's a longer one. Former US State Department and nuclear regulatory officials on Tuesday urged the US Department of Energy to reconsider a plan to use bomb-grade uranium in a nuclear power experiment, saying that its use could encourage such tests in other countries. And it's talking about TerraPower, which is one of the reactor companies. Are you aware or?
Yeah, I am aware of that. This is the proposal to test the reactor with 90%, 90+% enriched uranium. I saw a news article about it. I was told to be careful about the reliability of the report. I was a little surprised to see that. The United States, after the end of the Cold War, spent a lot of money trying to convince people not to have highly enriched uranium in their research reactors, which are research reactors the United States helped countries to get. That was the research reactor design. And bringing it back and sending other fuel and, spend a lot of money. Well, I think it was well spent. But then to go ahead and do this while you're telling other countries to not do it, if I might make an observation that's more general, do as I say and not as I do is not a very good approach. Especially the days when the United States could tell everybody what to do, whether you like it or not, are gone. And there were the days like that. It was the 50s, 40s, 50s, 60s, starting in the 70s. So it would be better to adopt a style of diplomacy where you didn't do that. That said, I don't know if they're actually going to do it. I have not seen anything from the DOE or from TerraPower saying they're going to do it. And I might say this molten salt reactor idea, please. I did a discussion on Science Friday. You can Google it, thorium reactors, long ago and 10 years ago, and you can see my take on molten salt reactors, which is what this would be about.
Okay, great. DOE and the NNSA want to change WIP's mission. They want to expand the footprint, extend the life by at least 60 years, and change what substances may be deposited. This is not due to DOE EM cleanup efforts. It is in anticipation of new pit production. Can you comment on this proposed plan?
Well, in a way, I've already commented, right? I said, I don't think new pit production is a good idea. So we can save ourselves that worry. But more generally, a lot of people in New Mexico oppose this. And I know the Southwest Research and Information Center was very material in making the whole process for transportation more safe, what kind of containers, what will happen in an accident. Then the repository opened. They've been wonderful watchdogs. And so the EPA made an agreement with the community and with the government. Talk about consent-based. Okay, so there was a consent-based process there. There was an official watchdog group in addition to the NGOs. And then it opened. There was a very specific contractual agreement. Now, if you're going to violate that, where are we? So even if you need another repository, you got to go through that process because, but here I saw that my friend Pam Kingfisher was on one of the participants. And I think we should refer to the indigenous leaders on this point. What is the US record of sticking to its word? And I think that's got to change because unless there's a serious trust in the process, and it will not help the larger repository effort, which I support, not the present effort, this consent-based stuff. It would not be a good thing. So I think if there's going to be a change in mission, it can't be imposed from the top. I think there shouldn't be a change in this contract in this way. It was a very important contract and it should be honored. even though it's a difficult situation, there's a lot of stuff that could be put down there, not just new. But it's important to resist that temptation and honor your deal with the community.
Yeah, absolutely. I think we have time for maybe one more question, and maybe this is a short one, maybe it's not, but how much does reprocessing increase the actual energy percentage of potential energy in nuclear fuel? What is the once through percent and what is the reprocessing percent? Do you know?
Yeah, I do know that. Why don't I do this? I will send you a couple of slides. I will add some slides. So the French are famous for recycling. In my calculation, when all is said and done, they will use less than 1% of the uranium. And in the current ones through, we use less than that, but not much less. So you don't gain a lot. And that's partly because the whole breeder reactor scheme did not work out. And using light water reactors for plutonium recycling is a losing proposition. Yeah, and they knew it going into it, but they did it anyway.
Yeah. Well,
I can answer one more.
One more?
Yeah.
There's a question about Fukushima. I attended a 10-year anniversary discussion, and what came out was that the residue was not only tritium, as the world has been told, but much more complex with other radioactive residues. Are you aware of that information?
Oh, yeah, I'm pretty aware. I'm actually on an expert panel trying to stop the TEPCO from dumping all that tritiated water into the ocean. And an expert panel retained by the Pacific Island countries, Pacific Island Forum. Yeah, the main problem is there are 3 molten reactor cores. At 3 Mile Island, there was one partially melted core. And so this problem is extremely complicated, extremely difficult, and totally unprecedented. At Chernobyl, they made it go away by just, building those structures around it. And I don't know what they're going to do. That's going to be a very hard problem. There's also so they process the water. They've got strontium waste. It's they've got a lot of contaminated dirt. So besides the water in the tanks, there's a lot of problems over there. Yeah. So thank you, people. I am so sorry I have to leave a little bit earlier than I agreed. Yeah, but I just have to go.
And we'll hope to have you back again.
Yeah, let's do this. It was good questions. I enjoy difficult questions. So let's do it again.